This is our machine design final project where we did a car door analysis by Andrew Jensen, Braden Patterson, and Drew Woodruff. We wanted to know how and why car doors break over their life cycle and why they need to be replaced often. Throughout a car door's life cycle, they need to be repeatedly opened and closed with small margin for error, making it an important component of a car. We conducted a fatigue failure analysis on the car door check and determined where the car door check was most likely to fail, which was at the fillet location due to the high stress concentration factor. We decided to use a 2015 Toyota Prius car door check. A picture of it is shown to the right with its dimensions and weight. After researching, the material of the car door check is SAE AISI 1020 steel.
First, let's look at what a car door check is before we get into any analysis. A car door check's purpose is to limit how far a car door can open. Here's a video showing the mechanism of a 2015 Toyota Prius door check. In this analysis, we want to find the number of cycles it would take before the check fails due to fatigue. To represent the check, think of it as a cantilever beam. Shown to the right is a representation of the check, where force is loaded, and the location of a fillet, which we believe would be the highest point of stress. Shown here are shear force and bending moment diagrams. The shear force diagram shows that the force is constant across the entire beam. Because we're looking at fatigue failure, we're assuming that any stress due to shear is negligible. The bending moment diagram shows how the moment is highest near the connection point, and the circle represents where the fillet is, and this is where the stress would be higher. In this analysis, we needed to calculate a stress concentration factor and a number of stress values. The stress values shown were calculated using equations and graphs from the Shigley text. These values are used to calculate fatigue factor of safety and the number of cycles before failure.
To find the fully corrected endurance limit, we had to determine the Marin factors and the test data endurance limit. For the Marin factors, the service factor is 0.8, the size factor is 1, the load factor is 1, the temperature factor is 1, and the reliability factor is 0.86. With a test data endurance limit of 235 megapascals, the corrected endurance limit turns out to be 163.18 megapascals. Also, our Goodman factor of safety is 1.0, and the number of cycles until failure is 1.9 times 10 to the 6th, which essentially means that the car door check will achieve infinite life under the current load. And here is our SN curve. As you can see from the red line, the load that the door check experiences will be under the endurance limit. In conclusion, with a factor of safety of 1.0 and a fatigue life greater than 10 to the 6 cycles, infinite life is predicted in the Toyota Prius front door check. However, if the part were to fail, it would most likely fail at the fillet due to having the highest stress concentration. Thank you for listening to our presentation.